Somewhere in the vastness of space, another version of our universe may be unfolding right now, shaped by different laws, different histories, and possibilities we can barely imagine. Welcome to the Drowsy Astronaut, where tonight we explore one of the most profound ideas in modern physics, the multiverse theory. An idea suggesting that reality may be far larger, stranger, and more layered than we ever expected. This is not fantasy, but emerging science, rising from equations in cosmology, quantum mechanics, and string theory, where parallel universes appear as natural consequences rather than wild speculation. In this video, we'll walk gently through each interpretation of the multiverse, moving slowly yet deeply so you can relax, drift off, or keep me as a quiet companion while you work on your own projects. But before we start, do me a small favor and let me know where you are tuning in from tonight. It is always a gentle pleasure to know so many corners of Earth gather here together. So now, settle in, breathe softly, and with your mind at ease, let us begin this journey together. The multiverse challenges everything we thought we knew about reality, forcing us to reconsider what we mean by universe, by existence, by the very nature of space and time itself. For most of human history, we believed our world was all that existed. Then we discovered other planets, other stars, other galaxies, and each discovery expanded our sense of what is real. Now physics suggests the ultimate expansion, that even our entire observable universe might be one bubble in an infinite foam, with other universes existing beyond our reach, forever invisible, yet mathematically necessary. This idea feels impossible at first, yet it emerges from our best theories, from the same mathematics that predicted black holes, gravitational waves, and the expansion of space, all of which we have now confirmed. So, the multiverse deserves serious attention, not as fantasy, but as a logical consequence of physics. And tonight we will explore where this idea comes from, what it means, and how scientists think about universes beyond our own. We will move slowly through four main types of multiverse: the quilted multiverse from infinite space, the inflationary multiverse from cosmic inflation, the quantum multiverse from particle physics, and the ultimate multiverse from mathematics. Each type has its own logic, its own evidence, and its own implications for what reality means, and together they paint a picture that is both unsettling and magnificent. But there is no need to feel overwhelmed or anxious about infinity, because we will take this gently, one layer at a time, letting each idea settle before we move to the next. Picture yourself floating in space, looking out at the night sky filled with stars, knowing that every point of light represents a sun, perhaps with planets, perhaps with life, each one a world of its own. Now expand that view to see entire galaxies, billions of stars clustered together, and then clusters of galaxies and superclusters, structures stretching across hundreds of millions of light years. This is our observable universe. Everything light has had time to reach us since the Big Bang, about 93 billion light years across, containing perhaps 2 trillion galaxies, each with billions or trillions of stars. It is almost incomprehensibly vast, yet the multiverse theory suggests this entire observable universe is just one small region, perhaps infinitely small compared to what lies beyond, like a single grain of sand on an endless beach. The basic concept is surprisingly simple once you let it settle in your mind. that our universe might not be unique, that the same physical processes that created our reality might have created others as well. We tend to think of the universe as everything that exists, all of space, all of time, all matter and energy, the totality of reality contained in one grand structure. But modern physics suggests this definition might be too narrow, that what we call the universe is really just our local region of a much larger structure, a multiverse containing many separate universes. These other universes might be physically disconnected from ours, separated by distance or by dimensional barriers, existing simultaneously with our own, yet forever beyond our ability to visit or directly observe. Different types of multiverse emerge from different branches of physics, and each has its own reasoning, its own mathematics, and its own way of explaining why multiple universes might exist rather than just one. The first type comes from cosmology and the possibility that space is infinite, continuing forever beyond what we can see. And if space goes on forever, then remarkable things follow from simple probability. The second type comes from cosmic inflation, the rapid expansion of space in the first moments after the Big Bang. And inflation theory suggests that this process might never stop completely, creating bubble universes eternally throughout an ever-expanding void. The third type comes from quantum mechanics and the strange behavior of particles at tiny scales, where every measurement might split reality into parallel branches, each one equally real, creating a vast quantum multiverse of possibilities. The fourth type is the most abstract, coming from pure mathematics, suggesting that every mathematically consistent structure exists somewhere as a physical reality, and our universe is just one equation among infinite others. Each of these multiverses sounds like philosophy or imagination, but they emerge from serious physics, from equations that successfully describe our universe and that logically extend beyond what we can directly observe. Scientists debate whether these ideas are testable science or untestable speculation, and the debate is healthy, pushing physics to clarify what kinds of evidence might confirm or rule out parallel universes. But the ideas persist because they solve real problems, explaining puzzling features of our universe that otherwise seem like impossible coincidences, and offering frameworks that unify different branches of physics. Tonight, we will explore each multiverse type carefully, moving from the most concrete to the most abstract, and we will see how each level expands our sense of what is possible, what is real, and what existence means. We will encounter ideas that challenge intuition, but we will approach them gently, always starting with simple concepts before building toward the strange, always pausing to let understanding settle. By the end, you will have traveled through layers of reality that most humans never consider, and whether you believe in the multiverse or not, you will understand why brilliant physicists take these ideas seriously. So take a slow breath, settle into comfort, and let us begin this peaceful voyage through infinity, through parallel worlds and quantum branches, through the vast landscape of possible realities. The observable universe is the starting point, the portion of space we can actually see and study, and understanding its limits helps us grasp why the multiverse idea emerges naturally from modern cosmology. Light travels at a fixed speed, about 300,000 kilometers per second, and nothing can travel faster. Not matter, not energy, not information, which means there is a horizon beyond which we cannot see. Our universe is about 13.8 billion years old, so light has had that much time to travel, and in principle, we can see objects whose light has been traveling toward us for that entire duration. But because space itself has been expanding during that time, those distant objects are now much farther away, about 46.5 billion light-years in every direction from us. This creates a sphere around us, our observable universe containing everything we can possibly see. And beyond that sphere lies more space, more galaxies, more stars, that their light has not had time to reach us yet. The important insight is that observers in those distant regions would have their own observable universes, spheres centered on their location, and their view would be different from ours, showing galaxies we cannot see. If space is infinite, then there are infinite such spheres, infinite observable universes, each one centered on a different point in space, each containing different galaxies but following the same physical laws. This is the first hint of the multiverse, the simplest version, emerging just from the combination of infinite space and the finite speed of light, creating multiple observable regions that can never communicate with each other. We will explore this infinite space multiverse in detail in the next part, but for now, just hold the image of countless bubbles of observability, each one like ours, scattered throughout infinite space. Beyond that lies the inflationary multiverse, where entire universes with different physical laws float like bubbles in an eternally inflating space, each one potentially different from ours in fundamental ways. Then comes the quantum multiverse, where every possible outcome of every quantum event actually happens, splitting reality into branches where all possibilities are realized, creating a tree of parallel worlds that grows constantly. And finally, the mathematical multiverse, where every mathematical structure exists as a physical reality somewhere, and our universe is just one equation made real, one pattern among infinite patterns woven into the fabric of existence. These four levels of multiverse form a hierarchy, each more radical than the last, but each connected to serious physics, emerging from theories that explain phenomena we can actually observe and measure. The multiverse transforms from science fiction to science when it becomes a prediction rather than an assumption. When theories develop to explain our universe naturally imply that other universes must exist as well. This is what makes the multiverse respectable despite its strangeness. It emerges from the math rather than being added artificially, appearing as an inevitable consequence of our best descriptions of reality. Whether the multiverse is real remains an open question, but the fact that multiple independent theories all point toward it suggests nature might actually be this extravagant, this generous with existence. Philosophers have long wondered whether reality could be different, whether the laws of nature are necessary or arbitrary. And the multiverse provides a framework where both might be true simultaneously. The laws might be necessary within each universe, but vary between universes, so that every possibility is realized somewhere, and the question becomes not what could exist, but what we happen to observe. This shift changes how we think about existence, from a single precious reality that easily might not have been, to an inevitable flowering of all possibilities, where existence is abundant rather than rare, and our universe is one manifestation of infinite creativity. Some find this comforting, the idea that everything that can exist does exist, while others find it vertiginous. But tonight we will explore it calmly, as a beautiful expansion of what reality might be. The first type of multiverse is the most straightforward, emerging from a simple question: does space go on forever, or does it eventually end? And if it goes on forever, then remarkable consequences follow. Our observable universe is finite, bounded by the cosmic horizon, beyond which light has not had time to reach us. But that boundary is just a limit on what we can see, not necessarily a limit on what exists. If space continues beyond our horizon, extending infinitely in all directions, then somewhere far away there must be other regions, other observable universes like ours, each one centered on a different location. These regions would be physically real, following the same laws of physics, but separated from us by such vast distances that we can never see them, never visit them, never communicate with them. This is called the quilted multiverse, named for how observable universes tile space-like patches in a quilt, each patch showing a different view of the same infinite fabric, and the fabric itself extends forever in all directions. The evidence for infinite space comes from observations of the universe's geometry, which appears to be flat rather than curved, and in general relativity, flat space can extend infinitely without contradiction. Measurements of the cosmic microwave background radiation, the ancient light from the early universe, show that space is flat to within 1% accuracy, consistent with infinite extent, though not proving it definitively. If space is infinite, then the implications become strange and wonderful, because with infinite space and finite arrangements of matter, everything that can happen must happen somewhere, infinitely many times. Think of it this way: there are only so many ways to arrange atoms in a given volume, a huge number but still finite, and if space goes on forever, then every possible arrangement must eventually repeat. This means somewhere far beyond our horizon there is another Earth, with another version of you living another life, making different choices, experiencing different outcomes, all equally real. In fact, there are infinitely many such copies, because in infinite space, every finite pattern repeats infinitely. So there are infinite Earths where you made different decisions, where history unfolded differently, where quantum randomness produced different results. Some of these copies are nearly identical to you, differing in only trivial ways, while others are very different, having diverged long ago through accumulated small changes, but all share your basic structure. The mathematics of this are straightforward once you accept infinity. If you have infinite trials of a finite system, every possible outcome occurs, and not just once, but infinitely many times. To see how far you would need to travel to find your nearest copy, we can estimate based on the number of possible quantum states in a human-sized region, which is enormous but finite. Physicists estimate this distance as roughly 10 to the power of 10 to the power of 29 meters, a number so large it defies comprehension, far beyond our observable universe, but still finite within infinite space. So your nearest identical copy exists, but is unreachably far, separated by distances that light would need far longer than the age of the universe to cross, effectively in a separate universe despite sharing the same space. These distant regions are not alternate realities in a mystical sense. They are simply distant parts of the same infinite space, as real as the room you are in now, just impossibly far away. The strange part is that everything you might imagine exists somewhere in this infinite space. Every book never written has been written somewhere. Every life never lived is being lived somewhere. Every possible history has unfolded somewhere. This level of multiverse is the most conservative, requiring only that space be infinite, which is consistent with observations even if not proven, and it emerges naturally from the simplest cosmological models. Some physicists find this version of the multiverse less controversial, because it does not require new physics, just infinite space and the probabilistic consequences of infinity applied to finite systems. Still, the implications challenge our sense of uniqueness and specialness. If infinite copies of you exist, does that diminish your significance? Or does it affirm that your pattern is fundamental enough to appear repeatedly throughout reality? Perhaps it is better to think of it this way. You are still unique in your local context, in the region of space you can affect, and the distant copies are so far away they might as well be in separate universes. The quilted multiverse also suggests that our observable universe is not special, that there is nothing unique about our location, our laws of physics, or our history, because the same patterns repeat everywhere in infinite space. This connects to the cosmological principle, the assumption that the universe is homogeneous on large scales, looking basically the same everywhere, with local variations but no privileged locations or special regions. If the universe is infinite and homogeneous, then every observable region sees roughly the same thing. Galaxies, stars, planets, structures, following the same physical laws, and our view is typical rather than exceptional. Observations support this picture on large scales. Galaxy surveys show the universe looks statistically similar in every direction, and the cosmic microwave background is remarkably uniform across the sky. But homogeneity breaks down on smaller scales, where local variations matter, and this is where the copies emerge, in the details of how matter clumped, and stars formed, and planets coalesced, and life evolved. In infinite space, these local details vary, exploring all possibilities, and somewhere every possibility is realized, creating a multiverse of variety within a universe of uniformity. The quilted multiverse does not require different laws of physics, just different outcomes of the same laws applied to different initial conditions, and this makes it testable in principle, though not in practice. We cannot travel to other observable universes within infinite space to confirm their existence, but we can test whether space is truly infinite by measuring its curvature more precisely, looking for signs of closure or topology. Future measurements might reveal that space curves back on itself, forming a finite shape like a sphere or torus, which would rule out simple, infinite space and eliminate this level of multiverse. But if space remains flat to ever higher precision, that would support infinity. And while not proof, it would make the quilted multiverse more plausible, more likely to be real. One puzzle with infinite space is the question of probability. How do we calculate the likelihood of events when infinite copies of everything exist, and what does probability even mean in such a context? If infinite copies of you make every possible choice, then every outcome occurs, and traditional probability breaks down because nothing is more or less likely. Everything happens with certainty somewhere. Physicists are still working on this problem, developing measures to compare infinities, trying to make sense of probability in infinite contexts. And the solutions involve subtle mathematical concepts that remain debated. For our purposes tonight, just hold the idea gently that infinite space might mean infinite versions of reality, all equally real, all existing simultaneously in different, unreachable regions. Picture the infinite universe as an endless ocean, with observable universes like islands scattered throughout. Each island a sphere of visibility about 90 to 3 billion light-years across, each containing galaxies and stars. The ocean itself is space, extending forever in all directions. And the islands are not separate places, but regions defined by light travel time, overlapping spheres centered on different observers. Between the islands, the ocean continues, filled with more galaxies and matter, following the same physics, and somewhere in that infinite expanse, every possible arrangement appears, every story unfolds. This is the quilted multiverse, the simplest level, requiring only infinity and patience. And it suggests that reality is far more abundant than we ever imagined, containing not just our universe, but infinite variations on the same theme. We move now toward the second level, the inflationary multiverse, where universes are not just distant regions of the same space, but separate bubbles with potentially different laws. And this emerges from the theory of cosmic inflation. But first, take a moment to absorb the first level, infinite space, filled with infinite observable universes, infinite copies of you and me and Earth, all existing simultaneously in one vast quilted reality. It is a peaceful thought in its way, suggesting that existence is generous, that the universe does not stop at our horizon but continues forever, and that every possibility is honored somewhere with existence. Rest with that idea as we prepare to explore the next level, where inflation takes us beyond just infinite space into a realm of bubble universes, each one a cosmos unto itself. Cosmic inflation is one of the most successful theories in modern cosmology, explaining several puzzles about our universe by proposing that space expanded exponentially fast in the first fraction of a second after the Big Bang. This expansion was not just rapid, but exponential, meaning space doubled in size again and again in incredibly short intervals, perhaps every 10 to the minus 35 seconds, for a brief period before slowing down. Inflation explains why the universe is so flat, so uniform, and so large, because the exponential expansion smoothed out irregularities and stretched space to enormous size, creating the homogeneous cosmos we observe today. The theory was developed in the 1980s by physicists including Alan Guth, André Linde, and others, and it has since been confirmed by observations of the cosmic microwave background, which shows exactly the patterns inflation predicts. But inflation has an unexpected consequence that leads directly to the multiverse. Once inflation starts, it might never completely stop, continuing eternally in some regions, even while ending in others, like our universe. Imagine space inflating everywhere at once, doubling in size again and again. But occasionally, in random locations, the inflation field decays, stopping the expansion and allowing normal space-time to form, creating what we call a universe. These pockets where inflation ends are like bubbles forming in boiling water. Each bubble contains a universe like ours with galaxies and stars, while the space between bubbles continues inflating exponentially, forever producing new bubbles. This process never stops because the inflating space grows faster than bubbles can fill it. So eternally into the future, new bubble universes are forming, each one potentially different from the others in fundamental ways. This is called eternal inflation, and it leads to the second level of multiverse, where each bubble is a separate universe, possibly with different physical constants or even different laws of physics than our own. The reason bubbles might differ comes from string theory and quantum field theory, which suggest that the inflaton field, the field driving inflation, can settle into different states when it decays, like a ball settling into different valleys. Each state corresponds to different properties of the universe that forms, different strengths of fundamental forces, different masses for particles, different numbers of dimensions, creating a vast landscape of possibilities. Our universe is one such bubble, where the inflaton field settled into the particular state that gives us our physics. But other bubbles have different states, different physics, and potentially radically different conditions, including some where life could never exist. The landscape of possible universes is staggeringly large. String theory suggests perhaps 10 to the power of 500 different possible vacuum states, each corresponding to a different possible universe, and eternal inflation samples all of them over time. Most of these universes would be sterile, unable to form stars or atoms or any complexity, but a tiny fraction would have conditions suitable for matter, structure, and potentially life. And we necessarily observe one of those rare cases. This leads to a natural explanation for fine-tuning, the puzzling fact that our universe's constants seem precisely set for life. If countless universes exist with random constants, then by pure chance, some will be life-permitting, and observers necessarily find themselves in those. Anthropic principle states that we should not be surprised to observe a life-friendly universe, because in a multiverse, only such universes contain observers. And this removes the mystery of why our universe seems designed for us. Each bubble universe in eternal inflation is causally separated from the others, meaning they cannot communicate or interact because the inflating space between them expands faster than light, creating permanent disconnection. Light or matter from one bubble can never reach another, so each bubble is effectively infinite from the inside, a complete universe unto itself, and the collection of all bubbles forms the Level 2 multiverse. From outside the bubbles, if such a perspective were possible, you would see an eternally growing fractal structure, with inflating space creating new volume faster than bubbles can fill it, producing infinite universes in infinite time. But no observer can take that outside view. We are trapped inside our bubble, and the other universes are forever beyond our observational horizon, existing in principle, but invisible in practice. The evidence for eternal inflation comes from the evidence for inflation itself, which is strong based on measurements of the cosmic microwave background that match inflation's predictions with remarkable precision. Observations by satellites like WMAP and Planck have measured the temperature fluctuations in the cosmic microwave background, finding patterns that match exactly what inflation predicts, providing strong indirect support for the basic inflationary mechanism. If inflation happened in our universe, and if the theory is correct, then eternal inflation is almost inevitable, because the mechanism that stops inflation here would not stop it everywhere, allowing it to continue in distant regions. Some physicists argue that eternal inflation is the natural outcome, more natural than inflation stopping everywhere simultaneously, because randomness and quantum fluctuations ensure that different regions behave differently. The challenge is that eternal inflation makes the multiverse not just possible, but inevitable. And if true, this means we can never observe most of reality, only our local bubble, which raises questions about testability. Can we test whether other bubbles exist, if they are forever beyond our horizon? Or does eternal inflation make predictions that cross the boundary from science into philosophy, from testable to merely logical. Some researchers are searching for evidence of bubble collisions, because if another bubble once collided with ours during inflation's early stages, it might have left an imprint on the cosmic microwave background, a bruise or pattern. Such collisions should be rare, but not impossible, and finding one would provide direct evidence that other bubble universes exist, making the Level 2 multiverse testable even if the bubbles themselves remain forever beyond reach. So far, no convincing collision signature has been found, but the search continues, and some anomalies in the cosmic microwave background, like the cold spot, have been speculatively linked to possible collisions, though other explanations seem more likely. Even without collision evidence, eternal inflation remains a serious possibility because it emerges naturally from standard inflation, which is itself well supported, and it provides a framework for understanding fine-tuning. The landscape of possible universes solves the puzzle of why our universe seems special, by making it one outcome among countless others, removing the need for design or miraculous coincidence, replacing uniqueness with statistical inevitability. This shift in perspective is profound, from seeing our universe as the universe to seeing it as one environment among infinite environments, most hostile to life, a few friendly, and we exist in one of the friendly ones by necessity. Eternal inflation also connects to the concept of the multiverse as a generative process, not something that exists statically, but something that is constantly creating new universes, an ongoing process of cosmic reproduction that never ends. Each bubble universe might itself contain regions that eventually undergo new inflation, creating bubbles within bubbles, a nested structure that could continue indefinitely, though this remains speculative and depends on uncertain physics. The mathematics of eternal inflation involves probabilities in ever-expanding space, where the volume of inflating regions grows exponentially, while bubbles where inflation ends form within it, creating a race between growth and nucleation. Inflation always wins this race because exponential growth outpaces bubble formation, ensuring that no matter how many bubbles form, more inflating space remains, and the process continues eternally into the future. Picture eternal inflation as a cosmic foam, with bubbles constantly forming in an ever-expanding substrate. Each bubble, a universe where inflation ended and normal physics began, and the foam itself growing faster than the bubbles can fill it. Our universe is one bubble in this foam, roughly 13.8 billion years old, having formed when inflation stopped here, while nearby regions of the foam continue inflating, already producing or soon to produce their own bubble universes. The foam extends infinitely in time and possibly in space, with no beginning and no end to the process. Just endless creation of universes, each one potentially different from all others, each one a complete cosmos. This vision is both humbling and inspiring, suggesting that existence is incredibly generous, that reality produces universes the way trees produce leaves, abundantly, constantly, with infinite variation and infinite possibility. Some find eternal inflation beautiful, a theory that makes existence abundant rather than precarious, while others find it disturbing, wondering whether science should accept theories that predict unobservable realms and infinite, unprovable entities. The debate continues among physicists, with some arguing eternal inflation is a natural prediction and others calling for alternative frameworks, but the theory remains influential because it emerges from well-tested physics and solves real problems. For tonight, we simply hold the idea gently, that our universe might be one bubble in an infinite foam, that inflation might never truly end, and that countless other universes might exist beyond our horizon. This is the Level 2 multiverse, more radical than Level 1, predicting not just distant regions with the same physics, but separate universes with potentially different physics, all created by the same eternal inflationary process that gave birth to our cosmos. Quantum mechanics is the physics of the very small, describing how particles and atoms behave, and it has been extraordinarily successful, predicting experimental results with incredible precision, yet it leads to one of the deepest puzzles in science. At quantum scales, particles do not have definite properties until they are measured. Instead, they exist in superposition, simultaneously in multiple states, like a coin spinning in the air that is both heads and tails until it lands. This superposition is not just ignorance on our part, but a fundamental feature of reality, confirmed by countless experiments showing that particles genuinely do not have definite positions or velocities until observation forces them to choose. The puzzle arises when we ask what happens during measurement. How does a particle in superposition suddenly become definite, collapsing from many possibilities into one observed outcome? And what counts as measurement? This is called the measurement problem, and it has troubled physicists since quantum mechanics was developed in the 1920s, with different interpretations offering conflicting answers about what measurement means and what reality is like between measurements. The standard Copenhagen interpretation says that measurement causes collapse, that the act of observation forces reality to choose one outcome from many possibilities. But this leads to questions about what counts as an observer. Does consciousness cause collapse, or does any interaction count as measurement? And if interaction is enough, then particles are constantly measuring each other. So when and how does definite classical reality emerge from quantum fuzz? These questions have no settled answers in the Copenhagen interpretation, and the ambiguity has led some physicists to explore alternative interpretations that avoid collapse, including the many worlds interpretation proposed by Hugh Everett in 1957. The many worlds interpretation says that collapse never happens, that superposition continues forever, and when we perform a measurement, reality splits into branches, each branch containing one possible outcome and one version of the observer. In this view, every quantum event causes the universe to branch, creating parallel worlds where all possibilities actually happen. And what we experience as measurement is simply our consciousness following one branch, while other versions of us follow other branches. This removes the measurement problem, because there is no special moment of collapse, just continuous branching, and every possible outcome is equally real, existing in parallel branches that cannot communicate, but are all part of the same quantum reality. The many worlds interpretation sounds like science fiction, but it is mathematically simpler than collapse theories, because it takes the Schrödinger equation, the fundamental equation of quantum mechanics, seriously and applies it to everything, including observers. If many worlds is correct, then the Level 3 multiverse exists, where every quantum event creates branches, and the number of parallel universes is unimaginably vast, far exceeding the Level 1 or Level 2 multiverses in sheer quantity. Every time a particle could go left or right, reality splits. Every time an atom could decay or not decay, reality splits. Every time light could reflect or transmit through a surface, reality splits into parallel versions. The splitting happens constantly, trillions of times per second just in the atoms of your body, creating a vast tree of parallel worlds that grows exponentially, with each branch containing a version of you experiencing one possible sequence of events. In some branches, you made different choices, said different words, lived different lives, and all these versions are equally real, existing in parallel quantum branches, experiencing their own realities that feel just as singular and definite as yours does now. This means that in the quantum multiverse, every possible outcome of your life actually happens. In some branch, you became an astronaut, in another, a teacher, in another, something else entirely, and all these versions coexist in the grand quantum structure. Every decision you agonized over was made both ways in different branches. Every missed opportunity was taken somewhere. Every path not chosen was walked by another version of you, and the full reality contains all possibilities. Some find this comforting, the idea that nothing is truly lost, that every possibility is honored with existence somewhere, and that the universe is generous enough to allow all outcomes rather than discarding all but one. Others find it unsettling, wondering whether their choices matter if all possibilities happen anyway. But many worlds advocates argue that choices still matter within your branch, affecting which future branches you will experience. The evidence for many worlds is indirect, coming from the success of quantum mechanics itself, which describes nature using the mathematics of superposition, and many worlds simply takes that mathematics literally, without adding collapse. Experiments confirm that particles truly exist in superposition before measurement, that they genuinely take multiple paths simultaneously, interfering with themselves in ways that only make sense if all possibilities are physically real until observation. The famous double-slit experiment shows this beautifully, where individual particles create interference patterns that require the particle to somehow go through both slits simultaneously, as if exploring all possible paths before arriving at the detector. Many worlds explains this naturally by saying the particle does take all paths, each path in a different branch, and what we see is the interference between those branches before they fully decohere and become separate worlds. Decoherence is the key concept that makes many worlds work, describing how quantum systems interact with their environment in ways that cause branches to separate, becoming effectively isolated from each other, unable to interfere, creating the appearance of definite classical outcomes. When a measurement occurs, the quantum system becomes entangled with measuring apparatus and environment, and decoherence splits the combined system into branches so quickly that interference between branches becomes impossible to detect, making each branch feel unique. This happens extraordinarily fast, typically within microseconds or faster for macroscopic systems. So by the time we are aware of a measurement result, the branches have already separated, and we experience only one outcome as real. But the other branches continue existing, equally real from the perspective of observers within them, each branch containing observers who experience different outcomes and who feel certain that their particular result is the only one that happened. The quantum multiverse is structured differently from the previous levels, not separated by vast distances or inflating space, but by quantum branching, all branches coexisting in the same space, but isolated by decoherence. You could think of it as reality having depth, perpendicular to ordinary space and time, with branches stacked in quantum configuration space, all present but unable to communicate, each one a complete history of the universe. Mathematically, this is described by the universal wave function, a single quantum state that encodes all branches simultaneously, evolving according to the Schrödinger equation, without ever collapsing, just continuously branching. Some physicists find many worlds elegant because it requires no special collapse mechanism, no mysterious role for consciousness or measurement, just straightforward application of quantum mechanics to everything, including observers. Critics argue that many worlds multiplies entities beyond necessity, creating uncountably many universes to explain measurements that collapse theories handle more simply. Though advocates counter that collapse requires adding new physics, while many worlds requires only taking existing physics seriously. The debate remains unresolved, with both interpretations having thoughtful defenders, and no experiment yet devised can definitively distinguish between them, because both make identical predictions for observable outcomes. What many worlds adds is a different ontology, a different picture of what exists, where reality is far richer than we experience, containing all quantum possibilities rather than randomly selecting one and discarding the rest. If many worlds is correct, then the level 3 multiverse is real, and you have countless parallel versions living out every possible quantum variation of your life, all existing simultaneously in different branches of the quantum wave function. Picture the quantum multiverse as a vast tree, with the trunk representing the early universe, and branches splitting off with every quantum event, creating a structure that grows exponentially in complexity, each endpoint a complete present moment. Every moment spawns countless branches as particles make quantum choices, and each branch itself splits further, creating a tree so vast that all possible histories of the universe exist as paths through its structure. Your consciousness follows one path through this tree, experiencing one sequence of branches, but other versions of you follow other paths, each one feeling just as singular, each one unaware of the others, each one living a complete life. The branches are real but separated, unable to communicate, so each version experiences reality as unique, despite being one thread in an infinite tapestry. And together, all branches form the complete quantum reality. This level of multiverse is perhaps the most personal, because it contains versions of you making different choices, living different lives, experiencing joys and sorrows you will never know in this branch, yet all equally you in some fundamental sense. Some find this thought peaceful, knowing that missed opportunities were taken elsewhere, that loved ones who passed still live in branches where quantum randomness produced different outcomes, that the universe preserves all possibilities. Others prefer to focus on their own branch, on the choices and experiences that define this version of themselves. And many worlds allows both perspectives, acknowledging parallel realities while affirming that this life, this branch, remains meaningful and unique to your experience. Whether many worlds is true remains an open question in physics, but the interpretation is taken seriously by many leading physicists, and it connects quantum mechanics to the broader multiverse story, suggesting reality branches at the quantum level. The fourth level of multiverse is the most abstract and philosophical, suggesting that every mathematically consistent structure exists as a physical reality somewhere. And our universe is simply one such structure, one equation among infinite others that have been made real. This is called the mathematical multiverse, or the ultimate ensemble, proposed by physicist Max Tegmark, and it asks a profound question. Why does mathematics describe physical reality so perfectly, unless physical reality actually is mathematics? Mathematics seems mysteriously effective in physics. Every law of nature we discover turns out to be expressible as mathematical equations. From Newton's gravity to Einstein's relativity to quantum mechanics, all written in the language of mathematics, as if nature were fundamentally mathematical. This unreasonable effectiveness of mathematics, as physicist Eugene Wigner called it, suggests a deep connection between math and reality, and the Level 4 multiverse takes this connection to its logical conclusion, proposing that they are the same thing. If physical reality is a mathematical structure, then other mathematical structures must also be physically real, existing as universes in their own right, and the collection of all consistent mathematical structures forms the complete Level 4 multiverse. Each mathematical structure that is logically consistent, that contains no contradictions, would exist as a universe with its own internal logic, its own entities, perhaps its own form of time and causality, though possibly very different from ours. Our universe corresponds to one particular mathematical structure, perhaps related to specific symmetries and equations in quantum field theory, but countless other structures exist as well, each one a universe unto itself, each one following its own mathematical rules. Some of these mathematical universes might contain consciousness and observers like us, while others might be sterile or so alien that concepts like space and time do not apply, existing as pure mathematical relations in abstract configuration space. This level of multiverse is controversial because it ventures into metaphysics, asking what existence means and whether mathematical structures can be said to exist without physical instantiation, questions that blur the boundary between physics and philosophy. Tegmark argues that the distinction between mathematical and physical existence is artificial, that to exist mathematically and to exist physically mean the same thing, and that our prejudice for physical reality stems from being embedded in one particular mathematical structure. From an external perspective, if such a thing were possible, there would be no difference between a universe described by equations and those equations themselves. The description and the thing described are one, and the universe is the mathematics made manifest. This suggests that existence is inevitable for any consistent mathematical structure. That logic alone ensures its reality somewhere. And the question is not what exists, but what structures contain observers capable of wondering about existence. The evidence for the Level 4 multiverse is philosophical rather than empirical, based on the effectiveness of mathematics in describing reality and on logical arguments about the nature of existence and mathematical truth. If our universe is mathematical, and if there is no reason to privilege our particular mathematical structure, then consistency suggests all such structures should exist, and the Level 4 multiverse follows from symmetry and parsimony rather than multiplying assumptions. Critics argue this is not testable science, but metaphysical speculation, because we cannot observe other mathematical universes or devise experiments that distinguish between the existence and non-existence of abstract mathematical structures as physical realities. Supporters respond that many scientific theories make unobservable predictions and that testability is not always direct, and that the Level 4 multiverse makes our own universe less mysterious by embedding it in a natural framework. One implication of the mathematical multiverse is that the laws of physics in our universe are not fundamental. They are just the rules of our particular mathematical structure, and other universes have different rules, different laws, different mathematics. This provides the ultimate explanation for fine-tuning, because if all mathematical structures exist, then all possible laws and constants are realized somewhere, and we observe our particular laws simply because this mathematical structure is complex enough to support observers. The Level 4 multiverse contains all other levels. The quilted multiverse is one mathematical structure with infinite spatial extent. Eternal inflation is mathematical structures with branching dynamics. And quantum many worlds is the mathematical structure of the universal wave function. So in some sense, Level 4 is the most complete, encompassing all other multiverses as special cases, though whether this makes it true or simply unfalsifiable remains debated among physicists and philosophers. Picture the mathematical multiverse as an infinite library, where every book represents a mathematically consistent structure, a universe following particular rules and containing particular entities, and the library contains every possible book with no contradictions. Our universe is one book in this library, written in the language of quantum field theory, with chapters describing particles and forces and space-time. But nearby books use different mathematical languages, describe different entities, follow different narrative structures. Some books describe universes with 5 dimensions of space, others with 11, some with different particles or forces, some with no concept of space or time at all, just pure relational structures defining mathematical entities. Consciousness appears in books whose mathematics is complex enough to support self-referential structures, and those conscious beings experience their mathematical universe as real, as physical, never suspecting they are living inside an equation in the infinite library. The beauty of this vision is that it explains why anything exists at all, because mathematical truth is necessary. Logical structures exist by the nature of logic itself, and physical reality emerges as the inevitable consequence of mathematical consistency. Existence is not a miracle or an accident, but a logical necessity. Every consistent structure exists because non-existence would be arbitrary, requiring some external principle to prevent it, and the simplest assumption is that all consistent structures are real. This removes the ultimate question of why there is something rather than nothing, because mathematical structures cannot not exist. They are true by logic, and physicality is simply what it feels like to be embedded in one such structure. Whether this answers the question or merely rephrases it remains open. But the Level 4 multiverse offers a framework where existence is abundant, necessary, and grounded in the bedrock of logic and mathematics itself. For tonight, we simply rest with this idea gently, that reality might be mathematics, that universes might be equations, and that existence might encompass all consistent logical structures, each one as real as ours in its own way. The mathematical multiverse is the most extreme version, pushing the concept of parallel universes to its logical limit, where not just other regions or branches, but entirely different mathematical realities coexist in the space of all possible structures. Whether it is true cannot be proven from within our universe, but it represents the culmination of multiverse thinking, the final expansion of what reality might be, encompassing everything consistent, everything possible, everything mathematically well-defined. And in that vastness, our universe remains special to us. The structure we inhabit, the mathematics we live inside, and whether infinite other structures exist, does not diminish the reality and meaning of our particular home. The simulation hypothesis offers a different path to the multiverse, suggesting that our universe might be a computer simulation created by an advanced civilization, and if one civilization creates simulations, then countless simulations must exist. This idea sounds like science fiction, but has been seriously discussed by philosophers and physicists, because if civilizations can create realistic simulations of universes, then statistical reasoning suggests simulated universes vastly outnumber the one base reality. Imagine a civilization becomes advanced enough to create detailed simulations of universes with simulated physics, simulated beings, simulated experiences, and suppose each simulation runs at high enough resolution that the beings inside believe their reality is fundamental. If that civilization creates many such simulations, and if the simulated beings eventually create their own simulations, then you get nested layers of simulation, with one base reality spawning countless simulated realities, each one containing simulated civilizations that create further simulations. In this scenario, the number of simulated universes quickly exceeds the number of base universes, and if you find yourself in a universe, probability suggests you are more likely to be in a simulation than in base reality, simply because simulations outnumber reality. This is called the simulation argument, formalized by philosopher Nick Bostrom, and it suggests three possibilities. Either civilizations rarely reach the technological level to create simulations, or advanced civilizations choose not to create them, or we are almost certainly in a simulation. If civilizations commonly reach simulation capability and often choose to create simulations, then the vast majority of conscious beings exist in simulated realities, and you should conclude with high probability that you are one of them unless you have evidence otherwise. The argument is unsettling because it suggests base reality might be rare, that most universes are nested inside other universes like Russian dolls, and that the deepest question becomes not what reality is, but what level of simulation we occupy. Could we test whether we are in a simulation? And several proposals have been made for experiments that might reveal computational artifacts, patterns in nature that resemble discretization or rounding errors that programmers might introduce to save computing resources. Some have looked for anomalies in the cosmic microwave background or in the distribution of high-energy cosmic rays, searching for patterns that might indicate the universe is computed on a grid rather than being continuous. So far, no convincing evidence of simulation has been found, but absence of evidence is not evidence of absence, and a sufficiently advanced simulation might be indistinguishable from base reality, leaving no detectable artifacts. Other proposals involve looking for inconsistencies in physical laws, or attempting to crash the simulation by performing computations too complex for the simulator to handle, though these ideas remain highly speculative and probably untestable. The simulation hypothesis connects to the multiverse because if simulations are possible, then countless simulated universes exist, each one as real to its inhabitants as our universe is to us, creating a multiverse of nested computational realities. Each simulated universe might have different physical laws set by the simulators who program it. So the simulation multiverse resembles the level 2 multiverse in allowing different physics, but the mechanism is computation rather than inflation. From inside a simulation, you cannot tell whether you are simulated or real, because all your experiences come from the simulation. All your measurements, all your physics experiments, all your thoughts are computed by the simulator and feel genuine. This raises profound philosophical questions about the nature of reality and existence. Whether simulated beings are truly conscious, whether simulated pain is real pain, whether simulated universes have moral standing equivalent to base reality. Most philosophers argue that consciousness and experience are substrate independent, meaning it does not matter whether your mind runs on biological neurons or silicon chips or in a simulation, if the information processing is the same. If this is correct, then simulated beings are genuinely conscious. Their experiences are real to them. Their suffering and joy matter morally, and simulated universes have the same ontological status as base reality from the perspective of those inside. This leads to the conclusion that the simulation multiverse is real in every meaningful sense. Even if our universe is a simulation, it is still the only reality we can ever access, and calling it simulation does not diminish its reality for us. The question of whether we are simulated becomes less important than understanding the structure of our reality, regardless of whether that structure is fundamental or computed, because to us it is all we can know. Some find the simulation hypothesis disturbing, suggesting we are just characters in someone else's game, while others find it comforting, suggesting that suffering might be limited or that the simulators might intervene in some beneficial way, though there is no logical basis for assuming benevolent simulators. The hypothesis also raises questions about the purpose of simulations. Are they created for entertainment, for scientific research, for historical analysis, or do they emerge as unavoidable byproducts of advanced computing civilizations? Without knowing the simulator's motives, we cannot predict their behavior, and we might be in a careful scientific simulation, a casual entertainment, or an accident within some larger computational process, with no way to determine which. For tonight, we simply hold the idea that our reality might be computation, and that if simulations are possible, then countless simulated universes exist, adding another layer to the multiverse story, another way reality might be more abundant than it appears. Picture the simulation multiverse as nested realities, each one computed by the level above, with base reality at the deepest level, then first-order simulations, then second-order simulations within those, and so on, stacking infinitely upward. We might be at any level in this stack, unable to tell whether we are in base reality or nested inside countless layers of simulation, and the question of our level might be meaningless because each level is equally real to its inhabitants. The simulation hypothesis suggests that reality is computational at its core, that universes are programs running on unknown hardware, and that the multiverse includes all possible programs, all variations of physical law that can be coherently computed. This connects to the mathematical multiverse, because computable structures are a subset of mathematical structures. And if reality is computation, then the simulation multiverse and mathematical multiverse might be describing the same thing from different angles. String theory is one of the most ambitious attempts to unify all forces and particles in physics, replacing point-like particles with tiny vibrating strings, and it naturally leads to multiverse ideas through its vast landscape of possible solutions. The theory requires extra dimensions beyond the familiar, 3 of space and 1 of time. Typically 10 dimensions total in string theory or 11 in M theory, and these extra dimensions are thought to be compactly curled up at every point in space. The size and shape of these extra dimensions determine the properties of our universe, the masses of particles, the strengths of forces, the number of particle types, so different configurations of extra dimensions produce different physics. String theorists initially hoped to find a unique configuration, one special shape that matches our universe perfectly. But instead they discovered the landscape, a vast space of possible configurations, perhaps 10 to the power of 500 different solutions. Each solution in the string landscape corresponds to a different possible universe, with different physical laws, different particle spectra, different force strengths, and the question becomes not why our universe has its particular laws, but how to select one solution from this enormous landscape. Eternal inflation provides a natural selection mechanism, because if inflation creates bubble universes constantly, then different bubbles can sample different points in the string landscape, creating a multiverse where all possible string configurations are realized somewhere. This combination of string theory and eternal inflation creates the level 2 multiverse, where each bubble is not just separated by distance, but has fundamentally different physics determined by how extra dimensions are configured in that region. Our universe corresponds to one point in the landscape, where extra dimensions have a particular shape and size, producing the particles and forces we observe. But other bubbles have different shapes, different physics, most likely hostile to life. The fine-tuning of our universe becomes explainable in this framework, because with 10 to the power 500 possibilities, some universes will have life-permitting physics by chance, and we necessarily observe one of those rare configurations because only they contain observers. This is a modern application of the anthropic principle, using the multiverse to explain what would otherwise seem like miraculous coincidences in our physical constants, by making them statistically inevitable across a vast ensemble. Critics argue that the landscape makes string theory unpredictive because it allows almost anything, and if you can explain any observation by saying it happens in some bubble universe, then you have not really explained anything at all. Supporters counter that the landscape is a prediction of the theory, not an assumption, and that statistical analysis of which configurations are most common might still make testable predictions about our universe's properties. Extra dimensions offer another route to parallel universes through brane cosmology, where our universe is a three-dimensional membrane or brane floating in a higher dimensional space, and other branes might exist nearby in the extra dimensions. These branes could be parallel universes in a literal sense, separated from us by tiny distances in extra dimensions, millimeters or less, but completely inaccessible because we are confined to our brain while only gravity can reach through extra dimensions. This could explain why gravity is so weak compared to other forces, because gravity dilutes into the extra dimensions while other forces are confined to branes. And if another brane floats nearby, it might affect our universe through gravity without being directly visible. Collisions between branes could create big bangs, starting new universes, and some cosmologists have proposed cyclic models where branes collide periodically, creating cycles of expansion and contraction, an eternal universe without a true beginning. The evidence for extra dimensions and string theory remains indirect. No experiment has yet detected extra dimensions or strings directly, but the theory remains popular because it unifies gravity and quantum mechanics, which no other framework successfully accomplishes. Particle accelerators, like the Large Hadron Collider, have searched for signatures of extra dimensions. looking for particles disappearing into hidden dimensions, or for miniature black holes that might form if extra dimensions exist, but so far, nothing has been found. This could mean extra dimensions are smaller than accessible energy scales, or that string theory is wrong, or that we need more powerful experiments, and the question remains open as research continues. For now, string theory's multiverse implications remain theoretical, emerging from the mathematics of the theory, and whether the landscape truly corresponds to physical reality or represents a failure of the theory to make unique predictions remains debated. Picture string theory's multiverse as a vast landscape of hills and valleys, where each valley represents a stable configuration of extra dimensions, a possible universe with its own physics, and the landscape contains countless valleys, perhaps more than atoms in our observable universe. Eternal inflation acts like a river flooding this landscape, filling different valleys at different times, creating bubble universes that settle into various configurations, and our universe is one valley among countless others. The valleys are separated by energy barriers, hills in the landscape, and transitions between valleys are rare but possible through quantum tunneling, so a universe might occasionally jump from one configuration to another, changing its physics. This dynamic landscape suggests that physical laws evolve, that the constants we observe might have been different in the past or might change in the distant future, though any such change would likely be catastrophic for existing structures. String theory also predicts particles and forces beyond what we have observed, including additional dimensions worth of particle types. And some of these might exist in our universe, but be very heavy, too massive to produce in current accelerators. Future experiments might detect these exotic particles, providing evidence for string theory. And if the theory is confirmed, then its multiverse predictions gain credibility, suggesting the landscape and eternal inflation describe reality accurately. Whether string theory is correct remains one of the great open questions in physics, but its multiverse implications are clear, predicting vast numbers of universes with different physics, all emerging from the same underlying theory of strings and extra dimensions. For tonight, we hold this layer of the multiverse gently, the idea that reality might have hidden dimensions, that our universe is one configuration among vast possibilities, and that the mathematics of strings and brains points toward multiplicity in the fabric of existence. The fine-tuning problem is one of the deepest puzzles in cosmology, referring to the fact that our universe's fundamental constants seem precisely calibrated to allow stars, planets, atoms, and life to exist at all. Change the strength of gravity even slightly, and stars would either burn out in seconds or never ignite. Change the strength of the strong nuclear force, and atomic nuclei would not form. Change the mass of the electron, and chemistry would fail. Dozens of physical constants and initial conditions must lie within narrow ranges for any complexity to emerge, and the probability that random settings would produce a life-permitting universe seems astronomically small, raising the question of why our universe is so special. There are three main explanations for this apparent fine-tuning: design by an intelligent creator, pure luck against overwhelming odds, or the multiverse where all possible settings exist and we necessarily observe a life-permitting one. The design explanation appeals to some, but is not scientific in the traditional sense, because it does not make testable predictions and raises the question of who designed the designer, pushing the mystery back without resolving it. The luck explanation is logically possible, but statistically unsatisfying, requiring us to accept that we won a lottery with odds of perhaps 1 in 10 to the power of hundreds or more, which many physicists find implausible. The multiverse explanation removes the puzzle by making fine-tuning statistically inevitable. If countless universes exist with random or varied constants, then some will be life-permitting by chance. And observers necessarily find themselves in those rare cases, because no observers exist elsewhere. This application of the anthropic principle is controversial, but it transforms fine-tuning from an inexplicable coincidence into a selection effect, something we should expect given that our existence requires life-permitting conditions. Consider gravity, one of the 4 fundamental forces. Its strength is set by the gravitational constant, and if this constant were larger by a factor of even a few thousand, stars would burn through their fuel in years rather than billions of years. Life requires stable stars, providing steady energy for billions of years. So a stronger gravitational constant would make life impossible. And similarly, if gravity were much weaker, stars might never form at all, leaving a universe of drifting gas. The electromagnetic force must also be balanced precisely. Too strong and atoms collapse, too weak and chemical bonds never form. And life requires complex chemistry, so the electromagnetic constant must lie within a narrow range. The strong nuclear force holds atomic nuclei together against electromagnetic repulsion, and if it were slightly weaker, only hydrogen would be stable, eliminating all heavier elements needed for chemistry and life. If the strong force was slightly stronger, protons would bind together directly, making hydrogen unstable, and again life could not exist. And this balance must be maintained to parts in thousands, a precision that seems remarkably unlikely. The weak nuclear force governs radioactive decay and certain nuclear reactions, and its strength affects stellar nucleosynthesis, the process by which stars create heavier elements, and changes would disrupt the production of carbon, oxygen, and other life-essential elements. The mass of the electron relative to the proton must also be fine-tuned. If electrons were much heavier, atoms would be smaller and chemistry would change dramatically, likely preventing complex molecules, and if electrons were lighter, atoms would be too large and diffuse. Even the cosmological constant related to dark energy appears fine-tuned. If it were much larger, the universe would expand too rapidly for galaxies to form, and if it were negative, space might recollapse before stars could form. These are just a few examples, and physicists have identified dozens of such fine tunings, constants, and initial conditions that must lie within narrow ranges, and the cumulative improbability seems overwhelming if we assume our universe is the only one. The multiverse offers a natural explanation. Different universes have different constants, sampled randomly or systematically from the landscape of possibilities, and we observe fine-tuned values because only such universes contain observers. This is not just speculation, but a prediction of eternal inflation and string theory, both of which naturally produce universes with varied physics, making the multiverse explanation for fine-tuning and inference from well-motivated theories rather than an ad hoc assumption. Critics argue that invoking infinite, unobservable universes to explain fine-tuning is extravagant, but supporters counter that the multiverse emerges from theories we have other reasons to believe, making it more economical than assuming miraculous coincidence or design. The anthropic principle provides the logical framework for understanding fine-tuning in a multiverse. stating that we should not be surprised to observe life-permitting conditions because our existence requires them, and observations are necessarily biased toward life-permitting universes. This principle comes in weak and strong forms. The weak version simply notes the selection effect that observers can only exist in life-permitting universes, so we should expect to find ourselves in one, regardless of how rare such universes are. The strong anthropic principle is more controversial, suggesting that the universe must have properties allowing consciousness to emerge, that observers are somehow necessary or fundamental. But this version is less widely accepted because it seems to privilege observers in a way physics typically avoids. For explaining fine-tuning the weak anthropic principle is sufficient, no need to assume observers are cosmically important, just that they can only exist where conditions permit. And this selection effect explains why we observe fine-tuning, preferring to find unique physical explanations for the constants. And research continues into whether the constants might be determined by deeper principles, perhaps emerging from symmetries or boundary conditions in a theory beyond the standard model. But so far, no such principles have been found that uniquely determine all the constants. And the landscape of string theory suggests that multiple solutions exist, making anthropic reasoning unavoidable if the landscape is real. The fine-tuning problem thus motivates the multiverse, providing empirical reason beyond pure theory to believe in multiple universes, because fine-tuning seems to demand explanation, and the multiverse offers the most natural scientific framework currently available. Whether this explanation is correct depends on whether the multiverse is real, and we will explore the evidence for that in the next part. But for now, we simply recognize that fine-tuning pushes physics toward multiplicity of universes. Picture our universe as a point in a vast space of possibilities, where each point represents different values of the fundamental constants. And most of the space is barren, with physics that produces nothing but drifting particles or collapsing space. Tiny scattered regions of this space are life-permitting, islands of complexity, where constants lie within narrow ranges, allowing stars, chemistry, and eventually observers to emerge. And our universe is one such island. In a single universe scenario, it seems miraculous that we landed on such an island. But in the multiverse, all points are sampled, all possible constants are realized somewhere, and observers necessarily find themselves on life-permitting islands because no observers exist elsewhere. This transforms fine-tuning from mystery to inevitability, from inexplicable luck to expected consequence of selection bias. And whether you find this explanation satisfying or unsatisfying, it represents the current frontier of cosmological thought. The multiverse seems untestable by definition, since other universes lie beyond our observational horizon. Yet physicists have proposed clever ways to search for evidence that might support or constrain multiverse theories, though none provide definitive proof. The most direct evidence would come from bubble collisions in eternal inflation. If another bubble universe collided with ours during the inflationary era, it might have left an imprint on the cosmic microwave background, a distinctive pattern that we could potentially detect. Such collisions should produce disk-shaped temperature anomalies in the microwave background, with a specific temperature profile depending on the collision's energy and timing. And researchers have searched for such patterns in data from satellites like Planck. Some candidate collision signatures have been identified, but none are statistically significant enough to be convincing. And most likely these patterns are just random fluctuations, but the search continues, and future missions might provide better data. The cosmic microwave background also contains other anomalies that might hint at multiverse effects, including the cold spot, a region about 10 degrees across that is unusually empty and cold compared to surrounding sky. Some physicists have speculatively suggested this could be evidence of another universe affecting ours, or a topological defect from bubble nucleation. But more conventional explanations, involving large voids or statistical flukes, seem more likely, and the cold spot remains unexplained but not confirmed as multiverse evidence. Looking for patterns in fundamental constants might also provide indirect evidence if we could measure how constants vary across our universe, and find that they are not truly constant but vary slightly in space. It might suggest we are in a bubble with local physics. So far, all measurements show constants are truly constant across cosmic distances, within observational precision, but improved measurements might reveal variations that would support bubble universe models and the landscape of string theory. Quantum experiments might test the many worlds interpretation, though distinguishing many worlds from other quantum interpretations is extremely difficult because they make identical predictions for measurement outcomes in almost all circumstances. Some proposed experiments involve maintaining quantum coherence in larger and larger systems, testing whether superposition persists at macroscopic scales as many worlds predicts, or whether collapse occurs at some threshold as other interpretations might suggest. So far, coherence has been maintained in increasingly large systems, molecules with hundreds of atoms, and even tiny diamonds. But no clear threshold has been found where classical behavior suddenly emerges, supporting many worlds but not proving it definitively. Another approach searches for interference between branches, which should be impossible after decoherence, but might be detectable with sufficiently sensitive experiments. Though most physicists expect decoherence is complete enough to prevent any such observation. The mathematical multiverse is essentially untestable because it makes no predictions that differ from a single mathematical universe. But its plausibility rests on philosophical arguments about the nature of existence and mathematical truth, rather than empirical evidence. Similarly, the simulation hypothesis is difficult to test, because advanced simulators would likely create simulations indistinguishable from base reality, and any test we devise might be anticipated and masked by the simulators. Some have suggested looking for computational limits or artifacts, patterns in physics that resemble discretization, or shortcuts that programmers might use. But such patterns could also arise from fundamental physics, making interpretation ambiguous even if anomalies are found. The strongest argument for the simulation hypothesis is logical rather than empirical, based on the reasoning that simulated universes should outnumber base reality if civilizations commonly create simulations, making it probable that we exist in one. String theory provides another avenue for indirect multiverse evidence, because if experiments confirm string theory's predictions about particles and forces, then the landscape of possible universes gains credibility as a natural consequence. The Large Hadron Collider has searched for supersymmetric particles predicted by many string theory models, but so far none have been found at accessible energies, which could mean they exist at higher energies or that string theory needs modification. Future colliders with higher energies might discover evidence for extra dimensions, perhaps particles disappearing into hidden dimensions, or gravitational effects that reveal higher dimensional structure which would support the string landscape and its multiverse. Even without direct detection, mathematical consistency of string theory provides some support, because string theory uniquely unifies gravity and quantum mechanics, suggesting it might be on the right track, even if experimental verification remains elusive. The falsifiability problem haunts all multiverse theories, because traditional science requires theories to make testable predictions that could in principle be proven wrong. And if other universes are unobservable by definition, how can we test their existence? Some physicists argue that indirect evidence is sufficient, that if theories with other motivations, like inflation and string theory, naturally predict multiverses, then the multiverse inherits credibility from those theories' success in explaining observable phenomena. Others maintain that unfalsifiable theories belong to philosophy rather than science, and that invoking unobservable entities to explain observations is not scientific progress, but a retreat from explanation into speculation. This debate continues among physicists and philosophers of science, and the resolution may require expanding our conception of what counts as scientific evidence, allowing indirect and statistical reasoning to supplement direct observation. One approach that might help is calculating probabilities from multiverse theories, predicting how likely various observations are given multiverse assumptions, and comparing these predictions to what we actually observe, looking for consistency or inconsistency. If multiverse theories predict that our observations are typical, that observers like us should commonly see universes like ours, then this supports the theory. And if our observations are predicted to be extremely rare, even in the multiverse, that counts against it. This has been applied to the cosmological constant, where the multiverse predicts we should observe a value small enough to allow structure formation, but not much smaller. And indeed, we observe a cosmological constant near this predicted range, which some see as evidence for the multiverse. But others argue such reasoning is circular or insufficiently precise, and that we cannot draw strong conclusions from a single observation of one universe, even if that observation is consistent with multiverse predictions. Perhaps the strongest evidence for the multiverse would come from theoretical unification. If a single theory elegantly explains all of physics and naturally predicts multiple universes, that would provide compelling, though indirect, support. We are not there yet, but progress in string theory and cosmology continues, and future breakthroughs might provide the unified framework that makes the multiverse an unavoidable prediction rather than an optional speculation. 4. Now we remain in an intriguing but uncertain position, with several independent lines of reasoning, all pointing toward multiverse, but no smoking gun evidence that definitively establishes its reality. The search continues, and part of the beauty of science is this ongoing quest, the willingness to explore ideas that push beyond current observation, knowing that future discoveries might transform speculation into established fact. Picture yourself as a scientist searching for traces of other universes, like searching for footprints on a beach that might have been left by someone walking just beyond the horizon, invisible but real. You examine the cosmic microwave background, looking for bruises from bubble collisions. You study quantum systems, looking for signs that superposition never collapses. You measure constants with ever greater precision, looking for variations across space. Each null result teaches something, constraining possibilities, and each anomaly might be the first hint of something extraordinary. though most anomalies turn out to have mundane explanations when examined carefully. The evidence for the multiverse remains circumstantial, suggestive, not definitive, but the search itself is valuable, pushing the boundaries of observation and theory, extending human knowledge toward the deepest questions about reality. We will soon explore the philosophical implications of the multiverse, what it means for identity, meaning, and existence, if infinite versions of reality truly exist. But first, let us rest with this question of evidence. Science has always progressed by proposing bold ideas, then testing them, and the multiverse is among the boldest, requiring new approaches to testing since direct observation may forever remain impossible. Whether the multiverse will be confirmed, refuted, or remain forever undecided, we cannot say, but the question itself stretches human thought to its limits, touching the very nature of reality. Take a breath and let this uncertainty feel peaceful rather than troubling. Because not knowing is part of the journey, and the cosmos keeps some secrets even from its most curious inhabitants. If the multiverse is real, it transforms not only physics, but philosophy, raising profound questions about identity, meaning, choice, and consciousness that have occupied thinkers for millennia, but now take on new urgency. We have explored the physics of multiple universes. Now, let us rest with the philosophical implications, the deep questions about what it means to exist in a reality where everything that can happen does happen somewhere. These questions have no definitive answers, but contemplating them can bring a strange peace, a sense that existence is abundant, that the universe is generous, that the great questions connect us to something infinite. As you settle deeper into comfort, let these ideas wash over you gently, not as problems to solve, but as mysteries to appreciate, as expansions of what reality might be, each one widening your sense of the possible. The first question concerns identity. If infinite versions of you exist across the multiverse, each making different choices and living different lives, which one is really you, and what does it mean to be an individual? In the Level Y multiverse, your copies are separated by unimaginable distances, each one identical to you, or nearly so, but forever unable to communicate or interact, and you will never know what their lives contain. In the quantum multiverse, new versions of you branch off constantly, with every quantum event creating divergent paths. And you share a common past with countless versions while your futures diverge infinitely. Are these other versions you, or are they different people who happen to share your body and memories? The question touches deep intuitions about personal identity, about what makes you uniquely yourself. One view says that you are the entire branching structure, that identity extends across all your quantum branches, and you are simultaneously living all possible versions of your life, even though each branch experiences only one path. Another view says that each branch contains a distinct individual, that identity follows each path separately, and while you share a common origin with your branches, you are no longer the same person once you diverge. Perhaps the truth is that identity was always more fluid than we assumed, that the self is not a fixed thing, but a process, a pattern, and patterns can repeat, branch, and diverge without contradiction. In this view, the multiverse does not threaten your identity, but reveals its true nature, showing that you are not a single thread, but a tapestry woven through many branches, connected to countless versions, yet experiencing one life at a time. The question of meaning arises naturally next. If everything that can happen does happen somewhere, does anything matter? Do your choices have significance? If alternate versions make all possible choices? This seems troubling at first, as if the multiverse undermines meaning. But consider, your choices still determine which branch you experience, which future becomes yours, and this remains meaningful within your experience. The fact that other branches exist does not diminish your branch any more than other people's lives diminish yours. You still face genuine decisions with genuine consequences for the life you will live. Some philosophers argue the multiverse actually increases meaning, because every choice is honored with existence somewhere. Every possibility is realized, and the universe says yes to all of them rather than discarding most. Free will takes on new dimensions in the multiverse context, because if all choices are made across branches, can we truly choose? Or are we just following predetermined paths through an already existing structure? In the quantum many-worlds interpretation, every choice creates branches. So rather than choosing between options, you are the mechanism by which all options become real, the branching point where possibilities separate into parallel realities. This can feel liberating rather than constraining. You are not struggling against determinism to make free choices. You are the process by which all choices are made, the point where potentiality becomes actuality across all branches. Whether this counts as free will depends on your definition, but it suggests that freedom might mean something different in a branching universe. Perhaps the freedom to be the origin of new realities rather than the freedom to select among them. Consciousness raises perhaps the deepest puzzles. How does awareness relate to the multiverse? Why do you experience one branch rather than all branches or no branches? What is the observer in the landscape of all possible observers? The anthropic principle tells us that consciousness can only observe universes compatible with its existence, that this does not explain why there is something it is like to be a conscious observer, why subjective experience exists at all. If consciousness is computation, as some philosophers suggest, then the same computation might run in many universes, and your experience might be realized across the multiverse, the same awareness instantiated in countless physical substrates. Or perhaps consciousness is fundamental, not reducible to physics, and the multiverse is the structure in which consciousness explores all possible experiences, each observer a point of view on infinite reality. The Boltzmann brain problem arises in infinite multiverses, suggesting that random quantum fluctuations should produce isolated conscious brains more often than they produce entire universes with evolved life. If this is true, then you are more likely to be a fluctuation brain with false memories than a real person in a real universe, which seems absurd but follows from straightforward probability calculations in some multiverse scenarios. Physicists take this problem seriously, using it to constrain multiverse theories, because any theory that predicts Boltzmann brains outnumber ordinary observers is probably wrong, and this limits which versions of the multiverse are plausible. The fact that we are not Boltzmann brains tells us something about reality, constraining the multiverse to versions where ordinary observers predominate, showing how the problem of consciousness connects to fundamental physics. Ethics in the multiverse context also requires reconsideration. If suffering happens in every possible way across infinite branches, does your effort to reduce suffering in this branch matter? Can you make any difference to total suffering? Some argue that you can only affect your branch, so ethics remains meaningful within your experience, and the fact that suffering exists elsewhere does not diminish your responsibility to reduce it where you can. Others suggest the multiverse makes ethics more important, not less, because if consciousness is real in all branches, then the sum of experience is vast, and any reduction of suffering ripples through the moral landscape with amplified significance. Perhaps the multiverse teaches that existence is abundant, that joy and suffering both exist in cosmic quantities, and our task is to cultivate joy and reduce suffering in the portion of reality we can touch, accepting that the whole is beyond our influence. The problem of measure haunts all these discussions. How do you count infinities? How do you compare the probability of being in one branch versus another when both contain infinite versions of observers? Standard probability theory breaks down with infinities because you cannot say one infinite set is more likely than another using ordinary methods, and this makes predictions and ethical calculations in the multiverse problematic. Physicists are developing new mathematical tools to handle these infinities, defining measures that assign relative probabilities to different regions of the multiverse, though no consensus has emerged on which measure is correct. This technical problem has profound philosophical implications, because until we solve it, we cannot rigorously reason about our place in the multiverse or calculate what we should expect to observe. Picture yourself floating in a vast ocean of possibility, where every wave represents a different version of reality. Each one real, each one containing observers who experience their branch as the only one. You are one point of awareness in this infinite ocean, connected to other points that share your past, diverging toward points with different futures, but experiencing only your local wave, your particular flow through the possibilities. The ocean is not cold or threatening, but vast and generous, containing all that can be, honoring every possibility with existence. And you are part of this abundance, one expression of infinite creativity. Rest with this image as we prepare to explore the criticisms of multiverse theory, knowing that even skeptics engage with these ideas seriously, and that healthy debate is how science and philosophy progress. These philosophical questions have no easy answers, but perhaps that is their value. They stretch our thinking, expand our categories, prepare us for a reality more strange and wonderful than common sense imagines. The multiverse is not just physics, but a new framework for understanding existence, and whether it is true or not, engaging with it deepens our appreciation for the mystery of being, for the strangeness of there being anything at all. Tonight we simply sit with the questions, letting them float in awareness without demanding resolution, because the deepest questions are not problems to solve, but mysteries to inhabit. And there is peace in mystery, in the recognition that existence exceeds understanding, that we are small enough to wonder and large enough to ask, participants in a cosmos that may be infinitely richer than we can ever know. Not all physicists accept the multiverse, and thoughtful criticisms have been raised about its scientific status, its explanatory power, and whether it represents progress or retreat in our understanding of nature. These criticisms are worth exploring carefully, not to dismiss the multiverse, but to understand its limitations, to see where the theory is strong and where it remains speculative, and to appreciate the healthy debate within physics. Science progresses through disagreement and scrutiny. Ideas that survive criticism become stronger, and ideas that fail teach us something valuable about where the boundaries of knowledge lie. As we explore these objections, let them deepen your understanding, not diminish your wonder, because even the skeptics are engaged with profound questions about the nature of reality. The central criticism concerns falsifiability, the principle that scientific theories must make predictions that could in principle be proven wrong. And if a theory predicts unobservable entities, can it be called science at all? Karl Popper established falsifiability as a criterion for science in the 20th century, distinguishing scientific claims from metaphysical speculation by whether they can be tested and potentially refuted. The multiverse seems to fail this criterion, because other universes are by definition unobservable, separated from us by cosmic horizons, or quantum decoherence, or dimensional barriers, forever beyond any possible measurement. Critics argue that invoking infinite, unobservable universes is not explanation, but a refusal to explain. That saying, everything happens somewhere, explains nothing specific and answers every question with the same meaningless answer. Defenders respond that falsifiability is not the only criterion for good science, and that many accepted theories make predictions about unobservable entities, from the interior of black holes to events before the Big Bang. The multiverse is not assumed, but predicted. It emerges from theories like inflation and quantum mechanics that we have independent reasons to believe. So if those theories are correct, the multiverse follows naturally. Moreover, the multiverse does make some potentially testable predictions about bubble collision signatures, about the statistical properties of constants, about the absence of Boltzmann brains, and these can, in principle, be checked against observations. Whether these tests are sufficient remains debated, but the multiverse is not arbitrarily unfalsifiable. It is connected to testable physics, even if its core claims about other universes remain beyond direct observation. Another criticism invokes Occam's razor, the principle that simpler explanations are preferable. And surely, one universe is simpler than infinite universes. So should we not prefer single universes explanations? But simplicity is not just about counting entities. It is about the complexity of the underlying laws. And if the laws that naturally produce one universe also produce infinitely many, then the multiverse is not an added complication, but an inevitable consequence. In fact, some argue the multiverse is simpler than a single universe, because explaining why our universe has its particular properties requires additional assumptions in a single universe framework, while the multiverse makes all properties equally natural. If you have to add special principles to prevent the multiverse and select our specific laws and constants, then those principles are complications, and the multiverse without such principles might be the simpler theory overall. The anthropic principle draws particular criticism, with some arguing that it is circular or unscientific to explain observations by saying we could only observe what is compatible with our existence. Critics worry that anthropic reasoning can explain anything, that whatever we observe can be justified by saying observers must observe it, which makes the approach unfalsifiable and therefore unscientific. Defenders counter that the anthropic principle is just a selection effect, analogous to noting that fish can only survey water because fish need water to live, which is not circular but simply acknowledging the conditions for observation. Used carefully, anthropic reasoning constrains which theories are viable. Because if a theory predicts observers should typically see something different from what we observe, that counts against the theory, making anthropic arguments testable in principle. Some physicists worry that the multiverse represents giving up, that instead of explaining why our universe has its particular properties, we simply say all properties exist somewhere and stop searching for deeper understanding. This seems like intellectual surrender, accepting that the constants are arbitrary rather than determined by some beautiful underlying principle, a disappointing conclusion after centuries of finding that nature follows deep mathematical patterns. Perhaps there is a unique theory that determines all constants, a final theory where nothing is arbitrary, where every property of our universe follows necessarily from mathematical consistency, and we should keep searching for it rather than accepting the multiverse. This hope motivates continued research into unified theories, into principles that might unequally determine the laws of physics. And it is a legitimate alternative to multiverse thinking that many physicists pursue. Alternative explanations for fine-tuning exist beyond the multiverse, including the possibility that the constants are not truly fine-tuned, but connected by relationships we do not yet understand, making apparent coincidences inevitable consequences of deeper physics. Some physicists explore whether the constants are dynamically determined, evolving over cosmic time to their current values through physical processes, or selected by some mechanism that favors life-permitting values without requiring infinite universes. Lee Smolin has proposed cosmological natural selection, where universes reproduce through black holes, each daughter universe having slightly different constants, and natural selection favors universes that produce many black holes which might correlate with life-friendliness. This is speculative, but shows that alternatives to the multiverse exist, that fine-tuning might be explained without invoking infinite unobservable universes, and the question remains open which approach will prove correct. The role of speculation in physics is itself debated, with some arguing that theoretical physics has become too disconnected from experiment, pursuing mathematical beauty rather than testable predictions. String theory, eternal inflation, and the multiverse have been criticized as unscientific in this sense, as elaborate mathematical constructions that may never be tested, representing physics becoming more like philosophy or pure mathematics. Others defend speculation as necessary for progress, pointing out that many now confirmed ideas, from atoms to black holes to gravitational waves, were once speculative, and bold theoretical work eventually leads to new experiments and observations. The right balance between speculation and observation is unclear, and healthy science includes both careful experimentalists and visionary theorists, each keeping the other honest, each pushing the field forward in different ways. Perhaps the deepest criticism is philosophical, that the multiverse transforms our universe from something to be understood into something arbitrary, one random outcome among infinite possibilities, which feels like a failure of explanation. When we explain something, we usually show why it is necessary, why it could not be otherwise given certain principles. And the multiverse instead says, our universe is contingent, accidental, one of countless equally real alternatives. This feels unsatisfying to many, as if the mystery has been dissolved rather than solved, as if saying all possibilities are real is a way of avoiding the question rather than answering it. But perhaps reality is contingent rather than necessary. Perhaps the deepest explanation is that existence is abundant, that the universe does not need justification, and that accepting this is maturity rather than surrender. The debate between multiverse advocates and critics continues, with both sides making important points, both contributing to our understanding of what science is and how it should proceed at its frontiers. Neither side has definitively won, and the question may remain open for decades or centuries, or it may be resolved by some unexpected discovery or theoretical breakthrough we cannot yet imagine. For tonight, we simply hold both perspectives gently, appreciating the multiverse as a possible description of reality, while acknowledging its problems, remaining open to alternatives, while recognizing the multiverse's explanatory power. Science thrives on such tensions, on the dialogue between bold speculation and careful skepticism, and engaging with both sides deepens our appreciation for how difficult and wonderful the quest for knowledge truly is. Picture the debate as a conversation among thoughtful people, each genuinely trying to understand reality, each bringing different intuitions and values, each contributing to a collective exploration that exceeds any individual perspective. The critics keep the field honest, demanding evidence and testability, preventing speculation from becoming dogma. And this is a valuable service even if the multiverse eventually proves correct. The advocates push boundaries, imagining possibilities beyond current observation, developing frameworks that might guide future discoveries. And this, too, is valuable even if some speculations prove wrong. Together, they model how knowledge advances. Through disagreement conducted respectfully, through ideas tested and refined, through the slow accumulation of understanding across generations of curious minds. We have traveled through many layers of the multiverse, from the quilted infinity of endless space to bubble universes with different physics, from quantum branches splitting constantly to abstract mathematical structures existing as reality. Now, as our journey approaches its end, let us reflect on what the multiverse means for how we live, how we understand ourselves, how we find peace in a cosmos that might be infinitely larger and stranger than we ever imagined. Whether the multiverse is real remains uncertain, but engaging with the idea has expanded our sense of what reality might be, and that expansion itself is valuable, opening our minds to possibilities beyond ordinary experience. Take a slow breath and let your body settle as we gather the threads of our exploration into a final reflection, a gentle meditation on existence, infinity, and your place in the cosmic landscape. If the multiverse is real, then existence is generous beyond measure, not sparse and precarious, but abundant and overflowing, with reality saying yes to every consistent possibility, honoring every mathematical structure with being. This should not feel threatening, but liberating, because it means the universe is not stingy with existence, not reluctant to create, but endlessly creative, endlessly generative, a fountain of reality rather than a fragile exception to nothingness. You are part of this abundance, one expression of infinite possibility, one pattern in the vast tapestry. And your existence is not an accident, but an inevitability in a multiverse where everything that can exist does exist. This transforms the question from "why do I exist?" to "how could I not?" in a reality generous enough to include all possibilities. Your particular pattern was certain to appear, certain to experience, certain to wonder about existence. The multiverse perspective suggests that nothing is truly lost. Every possibility is realized somewhere. Every path not taken is walked in some branch. Every loved one who passed continues in branches where quantum randomness produced different outcomes. This does not diminish your grief or joy in this branch, but it adds a layer of cosmic context, a sense that the full reality includes all outcomes, that your experienced reality is one perspective on something infinitely richer. Some find this comforting, a kind of cosmic reassurance. Others prefer to focus on their own branch, on the life they are actually living. And both responses are valid, both ways of making peace with infinity. The multiverse does not tell you how to feel. It simply expands the context in which your feelings occur, adding depth to experience without dictating what that experience should be. Your choices still matter in the multiverse, because even if all choices are made across branches, you experience only one branch, and your choices determine which branch becomes your experienced future. This is true whether you think of it as selecting among pre-existing branches or as creating branches through your decisions. Either way, your agency is real, your deliberation meaningful, your actions consequential for the life you will live. The existence of other branches does not make your choices arbitrary, any more than other people's choices make yours arbitrary. You still face genuine decisions with genuine consequences for you, and that is what matters for practical life. Perhaps the multiverse even increases the significance of choice, because each choice is a branching point, a moment where you become the origin of new realities, the pivot around which futures divide. Identity in the multiverse becomes more fluid, more expansive. You are not just this single thread, but a pattern that repeats across branches, that diverges and reconverges, that extends through the landscape of possibility. This can feel like losing something, as if the boundaries of self dissolve. But it can also feel like gaining something, discovering that you are vaster than you knew, connected to versions of yourself across infinite reality. The boundaries between self and other, between this life and possible lives, become more porous in the multiverse view, suggesting that separation is not fundamental, but a consequence of perspective, of being embedded in one branch. Perhaps the deepest truth is that consciousness is exploring itself through all branches, that you are one viewpoint in a vast exploration of possibility, one window through which existence experiences itself. Living with the multiverse means holding infinity gently, not trying to grasp it all or control it, but accepting that reality exceeds understanding, that the cosmos keeps secrets, that mystery is our permanent condition. This is not failure, but maturity, recognizing that the mind cannot contain infinity, that our concepts are finite tools applied to infinite reality, that peace comes from accepting limits rather than straining against them. The multiverse is an invitation to humility, to acknowledge that we are small enough to wonder, that our perspective is limited, that the full truth exceeds anything we can think or say. And in that humility there is rest, the rest of not needing to understand everything, of letting the mystery be mysterious, of floating in not knowing, as in a peaceful ocean. Consider what changes if the multiverse is real, and what stays the same, and you may find that more stays the same than you expected, that the infinite context does not transform daily life, but illuminates it from a new angle. You still wake and sleep, still love and grieve, still face choices that feel meaningful, still experience a singular life that is precious precisely because it is yours, regardless of how many other lives exist elsewhere. The multiverse adds layers, but does not subtract. Your joys are not diminished by being one among infinite joys. Your sorrows are not invalidated by existing alongside infinite sorrows. Your life is not rendered meaningless by the existence of other lives. Meaning is not a finite resource that must be divided. It arises fresh in each experience, in each moment of awareness, and infinite experiences mean infinite meaning, not meaning diluted to nothing. Perhaps the most beautiful implication of the multiverse is creative generosity, that reality creates abundantly, does not hoard existence but shares it infinitely, that the universe is fundamentally generous, fundamentally affirmative, saying yes to all possibilities. This transforms the cosmos from cold emptiness to creative fullness, from indifference to generosity, from absence to presence, and we are part of this generosity, expressions of this cosmic yes. Every star, every galaxy, every universe is an expression of this creativity. And you too are such an expression, brought into being by the same generosity that brings everything into being. One jewel in an infinite treasury. There is peace in being part of something so generous, in knowing that existence did not have to struggle into being, but flows freely, that reality is abundant, that the source is infinite. As we prepare to end this journey, let these ideas settle softly, not as conclusions demanding agreement, but as possibilities inviting contemplation, as expansions of imagination that might bring peace. The multiverse is not proven, perhaps can never be proven, but engaging with it has stretched your sense of what is possible, and that stretching itself is valuable, regardless of the theory's ultimate truth. You have traveled through infinity tonight, through layers of reality most humans never consider, through quantum branches and bubble universes and mathematical structures, through the landscape of all that might be. And now you return to your singular experience, to this moment, this breath, this body, resting in this place, the one perspective you actually inhabit, precious and irreplaceable despite infinite multiplicity. The Drowsy Astronaut floats through the cosmos, exploring not with spacecraft, but with thought, traveling not through ordinary space, but through the space of ideas, discovering not planets, but possibilities. Tonight we have explored farther than any physical journey could take us, to the edges of reality and beyond, to parallel universes and mathematical existence, to questions that touch the deepest mysteries. And now the exploration rests, the mind settles, the thoughts become gentle clouds drifting across awareness, the vast ideas becoming peaceful contemplation rather than active investigation. There is nothing more you need to do, nothing to solve or understand or figure out. Just rest, just be. Just let the infinite cosmos hold you as you drift towards sleep. Wherever you are in the multiverse, this version of you is here. In this moment, in this quiet space, having traveled through ideas that expand the mind, now returning to the simple experience of resting. Across infinite branches, versions of you are also settling, also drifting towards sleep, connected to you in pattern if not in substance, sharing this peaceful moment across the quantum landscape. You are not alone, even if you are singular. You are part of something vast, something that includes all possibilities. And that something is at rest now. That something is peaceful. Let the multiverse be a lullaby of abundance, singing that existence is generous, that reality is creative, that you belong to something infinite, that asks nothing of you but to be. The stars outside are distant suns, each one perhaps with planets, perhaps with life, perhaps with beings wondering about the multiverse as you have wondered tonight. And beyond those stars are galaxies. And beyond those galaxies are more galaxies. And perhaps beyond our observable universe are other universes, other bubbles in the inflating foam, other branches in the quantum tree. It is all one reality, all one existence, vast beyond comprehension, generous beyond imagination, and you are woven into it. One thread in infinite tapestry, one note in infinite symphony. Rest now in that belonging, in the peace of being part of something that transcends understanding, something that existed before you and will continue after, something that holds all possibilities in its infinite embrace. Your eyes are heavy now, your thoughts are slow. The journey through the multiverse has been long, and sleep approaches like a gentle tide, rising slowly, irresistibly, welcomingly. Let the concepts dissolve into images. Let the images dissolve into feelings. Let the feelings dissolve into pure rest, into the darkness behind closed eyes, into the approach of dreams. Tomorrow, the world will still be here, with its questions and mysteries, its possibilities and limitations. But now is for rest, now is for surrender, now is for the peace that comes after a long journey. You have explored infinity tonight, and infinity will still be there when you wake, patient and vast, waiting to be wondered at again. But now you rest within it, cradled by its vastness. Good night from the Drowsy Astronaut. May your dreams be peaceful, may your sleep be deep, may you drift through the night sky of your mind with the same wonder we have shared tonight. The multiverse holds you gently, one precious awareness among infinite awarenesses, one dreamer among infinite dreamers, all resting together in the cosmic night. Sleep now, sleep well. The universe is vast, but you are home. The questions are infinite, but you need no answers tonight. The possibilities are endless, but this moment is complete. Good night, and may you find in sleep what the multiverse offers in waking. Infinite peace, infinite rest, infinite belonging to something greater than yourself, holding you now and always as you drift softly into dreams.